specification. Let me make something clear. I'm not trying to prove that a cheap laptop can defeat the world's most powerful AI. I want to discover something more practical. Can it perform work that people actually need? Most AI tools do not truly run on our computers. When we enter a prompt, it travels across the internet to computers owned by another company. Their servers process it, and the answer returns to us. In other words, your computer is displaying the intelligence. It is not producing it. That difference matters. So today, I'm changing that relationship. I will install an AI model directly on this laptop. Then I will disconnect the internet and give it real work. If it fails, you will see it. If it succeeds, you will see that too. But there is a problem. Before this laptop can answer a single question, I must choose a model small enough to fit but intelligent enough to be useful. This is where things get interesting. This laptop cannot run just any AI model. Choose one that is too large and the computer could become extremely slow or fail to load it completely. But choose one that is too small, and it may not be intelligent enough to help. So, we need a balance. Local AI models come in many sizes. You may see labels such as 1 billion, 3 billion, 7 billion, or 14 billion parameters. Generally, larger models can perform more difficult work, but they also need more memory and processing power. Keep that trade-off in mind. More capability usually requires more hardware. Think of it like choosing luggage for a small car. A large suitcase may carry more, but it is useless if it cannot fit inside the car. AI models work in a similar way. The most powerful model is not always the right model. What matters is what your computer can carry. My laptop has 16 GB of RAM, or you may call it system memory. But Windows and my open applications are already using most of it. That means the AI cannot use all the memory listed on the computer's specification sheet. This part right here is extremely important, but it's usually easy to overlook. It changes which models can run safely. I could start downloading models and hope that one works. But some of these files are several gigabytes. Guessing would waste time, data, and storage. So, I'll use a tool called Mamilens to narrow down the options. Mamilens allows you to find the right local AI model for your computer and task. Simply input your system specification, and Mamilens recommends a model, the software to run it, and clear installation steps.
Go to Mamilens and input my system information. I will select everyday laptop. My operating system is Windows. I have a 16 GB of memory. I have a small GPU, so I'll select NVIDIA. My GPU is not listed among the GPUs here, so I will simply type the name of the GPU. My GPU is Quadro MM. It's an NVIDIA GPU, so I'll select NVIDIA. Then I'll select the VRAM. The GPU memory is 4 GB. Next, I'll select the task I want to do. General writing coding. The context window. I'll select the context. Then you have three options: fast conversation, balance, compatibility. First, I'll select balance. We want something that balances on our system. So it gives us the summary of what we have over here. I'll click show me 3 model match, and Mamilens show 3 models that can run on a system. The first is the recommended model. This is the one that is recommended. The best balance model that will go for a task. And then we have the fastest. The fastest that will run for our task is this one, Nemotron 3 Nano 4B. And then we have optional. This one is for the highest intelligence. We want an optional, but we need more intelligence. So this one is optional. Down here, you can compare the models. 24 billion parameter is 9 GB. The file size on this is approximately 2.5 GB. Nemotron 3 Nano 4B, it will take about 9 GB of system RAM. And the file size is approximately 2.8 GB. We have Llama 3.8B will consume about 11 GB of our memory, and the file size is approximately 4.9. So let's make a choice. Let's pick this one. So we would choose Qwen 3 4B. We click choose.
On paper, this model should fit. It should run without a dedicated data center GPU, and it should be capable enough for our tests. But should is not proof. There is only one way to know. We have to run it.
We can move to the next step, which is picking an engine. The moment I click on choose engine, I immediately land in the choose engine section. So I will select one person. So I will select personal chart, one person, beginner. LM Studio is already recommended. So over here, you see LM Studio. So what I will do is I will simply click on official download and I land on the official download page. Over here, we have LM Studio Bionic system. This is an AI agent like Cloud Code codex that lives on your system and can do work for you. But what we want right now is this download LM Studio. So I'll simply click on download LM Studio for Windows. And there we go. I will open the download folder and double click it, install it like any other Windows application. I agree, next, install.
The model is ready to download, but downloading it is only the first step. The real test begins when this laptop tries to load billions of parameters into its limited memory. That is the moment when things could go wrong.
Open LM Studio. Click on this robot and magnifier icon over here. Paste in the model we got from Mamilens and press enter. Let's take this one, Qwen 3 4B thinking. So we're going to click on this and then click on download. The model size is 2.5 gigabyte on this. So we will click on download and let's go grab some coffee and wait for it to download.
After about 15 minutes, the download is not yet finished. The laptop is still responsive and the fan remained loud. I'm still waiting for the amazing part, loading the model into my computer limited memory. Before opening LM Studio, the laptop was already using 6.9 gigabytes of its 16 gigabytes of memory. That left 8.9 gigabytes available for the software and the model. Opening LM Studio increased memory use to 7.6 gigabytes. The software itself had taken approximately 700 megabytes before any model was loaded. But the real change would happen when the model entered memory. Before loading the model, the laptop was using 7.6 gigabytes of memory. As the model loaded, the graph began to rise. Memory usage increased to 10.2 gigabytes, 64% of the laptop's usable memory. The model added approximately 2.6 gigabytes to memory use, but the system still had 5.7 gigabytes available. The laptop did not freeze. It did not run out of memory. And then, the model loaded successfully. Something else was happening. The NVIDIA graphics processor still showed 0% activity in this capture. This suggests that the model was being held mainly in the laptop's system memory rather than actively using the dedicated NVIDIA GPU at that moment. The model had loaded, but we still needed to test its speed. The model loaded successfully, and the laptop still had 5.7 gigabytes of memory available. But loading is not the same as working. The model is loaded, but that alone does not prove that this laptop can run AI locally. LM Studio is still connected to the internet, and a model that takes several minutes to answer is not very useful. So, this test has two conditions. It must work offline, and it must respond at a usable speed. First, I disconnect the laptop from Wi-Fi. To make sure the internet is really gone, I open the browser and try to load a website. The website does not load. This laptop is now offline. The internet is gone, but LM Studio remains open. The model is still inside the laptop's memory. If it answers now, that answer can only come from the model running on this machine. No cloud, no remote server, just this laptop. I start with a simple task. I ask the model to explain local AI to a 13-year-old using only 3 sentences. I submit the prompt. 4 seconds later, the first word appears. The model continues generating until the complete answer appears 26 seconds after I submit the prompt. The laptop is producing this response locally. While the model generates its answer, memory usage rises to 12.3 gigabytes, 77% of the laptop's usable memory. The processor reaches 48%. The integrated Intel graphics reaches 25%, but the largest workload appears on the dedicated NVIDIA graphics processor, which reaches 98%. The laptop is working hard, but it is still responding. When the model is loaded but waiting, memory usage sits at 10.2 gigabytes, and the NVIDIA GPU shows almost no activity. When generation begins, memory usage rises by approximately 2.1 gigabytes, and the NVIDIA GPU climbs to 98%. Loading the model and using the model are two very different workloads. I asked the model to explain local AI to a 13-year-old using 3 simple sentences. The answer compares local AI to a smart helper that works directly on your device. It explains that information does not need to travel to a distant computer, and it connects that idea to privacy. The language is simple, and the answer follows the instruction. The test works. This laptop loads a 4 billion parameter model and produces a complete response in 26 seconds. It uses 12.3 gigabytes of memory and pushes the dedicated NVIDIA GPU to 98%. The laptop is working close to its limits, but it does not freeze, and the model completes the task. This machine can run local AI, and it does all of this without an internet connection. But answering one simple question does not make an AI model useful. Can it summarize a document? Can it write professional content? Can it reason through a problem? And can it produce working code? Those tests require a separate experiment. The model is loaded, the laptop is responding, and local AI is running on this machine. Now we need to discover whether it can do real work. In part 2, I test this model with writing, document summarization, reasoning, and coding. Subscribe now and turn on notifications so you do not miss the next video. Part 2 is coming next, and that is where we discover whether this laptop can do real work.